SwayamPrabha. Digital India. Educated India.
Hello and welcome to the 14th lecture of Machining Science course. So, we were discussing the tool wear and tool life. We have seen that Taylor's tool life equation, which is one of the very basic tool life equation on the tool life, that relates the tool life with the parameter like cutting velocity. And then we said that the extended tool life equation, Taylor's extended tool life equation relates the tool life not only to the cutting velocity, but also to the feed and the depth of cut. Well, and also we said that on the tool life, maximum effect will be of the cutting velocity followed by feed and then by the depth of cut, because we have seen that experimentally the powers of the velocity is more than the power 1 by n, which is more than 1 by n 1 and which is more than 1 by n 2. This is how, if we see this is how we have said in the last lecture. Now, let us see the factors or the variables affecting the tool life. These are the 5 factors which are the cutting conditions, tool geometry, tool material, work material and the cutting fluid. They affect the tool life, and how they affect the tool life we will discuss it right now. Effect of tool geometry, let us say rake angle. Increasing the rake angle, we know that reduces the cutting force and the cutting temperature. Therefore, it resulting in the increased tool life. This we have discussed while discussing the selection of the rake angles. So, increasing the rake angle, it will reduce the force, it will reduce the cutting temperature and the tool life will be increased, and the vice versa. However, for large rake angle, the edge is weakened, resulting in the increased wear due to chipping of the cutting edge, and the tool life decreases. So, therefore, there is an optimum value of the rake angle at which the tool life will be maximum. Increased wear is also due to larger temperature, since the tool becomes thinner and the area available for heat conduction or the material available for the heat conduction will be less. This also we have discussed earlier. These conditions give an optimum rake angle which gives the maximum tool life, as I said. Higher is the strength of workpiece material, lower is the value of optimum rake angle. It is obvious. If the strength of the workpiece material is higher, in that case the force required will be more, and then it will reduce the tool life. Now, the flank angle, increasing the flank angle reduces rubbing between the tool and the workpiece, and hence it improves the tool life. So, while increasing the flank angle, as we have discussed earlier also, the cutting angle reduces and the tool again weakens, that reduces the tool life. Optimum value of flank angles is also affected by the feed rates. Higher is the feed rate, lower is the optimum value of the flank angle. The flank angle therefore, should be low if higher feed values are used. So, these are the recommendations which are theoretically as well as experimentally obtained. For example, here if you see, these are the curves that I have shown it earlier, that is, this is a similar curve to the tool life and the cutting velocity we have seen earlier. So, here what is shown here, that since on the tool life we have the effect of cutting velocity, feed and together they will actually increase the cutting temperature. So, here what is shown is that the relationship of the cutting temperature theta on the tool life, which jointly, I mean which combiningly saying that this is the effect of the cutting speed, feed and the depth of cut, because in terms of temperature all these three will enhance the temperature if they are increased. Okay. Now, here what is shown that the rake angle, as we are increasing the rake angle, initially the tool life is increasing, but then afterwards it decreases because the tool gets weakened, and if we say that this is the harder material than this, this is the strength of material, in that case the optimum value of the rake angle will be lower. Okay. So, earlier conclusion that we have made, that optimum value of flank angle is also affected by the feed rates, all right. And here we have said that higher is the strength of work material, lower is the value of the optimum rake angle. So, this is what is shown here. Now, here it is the flank angle. So, as we are increasing the flank angle, initially the tool life is increasing, as we said, because the rubbing is less, but afterwards the tool again weakens and the tool life decreases. And as the feed is increasing, let us say this is the maximum feed, this is lower than F1, this is lower than F3. So, with that the optimum flank angle that we will be getting should be less. So, if F1 is more than F2 then more than F3, then the optimum value of the flank angle will be less, delta 1 will be less than delta 2 than delta 3. Now, on the tool and the work material, the phenomena is very interesting in the sense that tool work material must be at least 35 to 58% harder than the work material. Okay. This has been established by the experiments, and the high strain rate of deformation and the elevated temperature of the work material complicate the situation in a way that with the increase in machining speed, the temperature of both the tool and the work material increases. Okay. Machining zone temperature is increasing as the machining progresses, as the cutting velocity increases. This is increasing the temperature of the tool and the work material, resulting in a lowered effective hardness of the tool. Unfortunately, the expected fall in the hardness in the work material is neutralized or compensated by the higher rate of deformation. See, you understand that higher rate of deformation means what? High resistance to the deformation, that is high strength. Okay. So, what is happening is that more the plastic deformation is being is imparted to the workpiece, more will be the resistance. So, the apparent strength of the workpiece is increasing as if. Okay. So, therefore, at a higher temperature, the tool and the workpiece material both are getting the same temperature, but the tool is thermally getting softened because the thermal softening of the workpiece does not happen because of the strain hardening. Because the more deformation, more plastic deformation is imparted to the workpiece is having the reaction in terms of increased strength. So, therefore, the tool wears out more, and therefore, the 30% to 58% more hardness is required for the tool material than the workpiece material. In general, harder the work material, higher will be the tool wear rate and lower will be the tool life. This is understood. This I already said to you earlier. Now, let us see the effect of the cutting fluid. Cutting fluids are primarily used for decreasing the cutting temperature and the chip tool interface friction. So, there are two functions of the cutting fluid: to decrease the temperature and to decrease the friction between the chip and the rake face of the tool. They also serve to keep the workpiece cool to avoid thermal expansion, provide a rust proof layer on the finished surface and remove chips from the machining area. These are known. Cutting fluid should have high specific heat and good thermal conductivity. This is also understood, so that it actually takes out the heat from the machining zone. A chemical constituent to form weak junctions, so that built up edge does not happen, because built up edge happens because of the nascent surfaces. If the nascent surfaces are covered with a layer, they cannot get welded, and therefore, there is no built up edge formation. So, this is the mechanism. Should have a low viscosity, because it has to penetrate. If it is very thick, very high viscosity, in that case it cannot penetrate the machining zone, and small molecular size, so that it can penetrate easily, non-corrosive and inexpensive. Okay. At a very high speed, coolant is inefficient, because it cannot get enough time to reach the machining zone, and also it cannot get into the machining zone because of that wedge which is formed by the tool and the workpiece and the chip. At that wedge, when the when the cutting fluid is passed at a high speed, it actually creates a thermodynamic or sorry the hydrodynamic force, and because of the hydrodynamic force it actually that force forces back the cutting fluid from the zone, and it does not permit the cutting fluid to reach. So, these are the two reasons basically because of which the at higher speed the tool the cutting fluid is not very effective. Let us give you some numerical examples. These are self explanatory. Now, this is the practical implementation of whatever we have learned. For example, tool life test in turning yields the following data. At this speed the tool life is given, at another speed the tool life is given. You have to determine the n and c values of the Taylor's tool life equation. Based on your equation, compute the tool life for a speed of 90 meter per minute and the speed corresponding to a tool life of 20 minute. Okay. So, you can see that you can get two equations, Taylor's tool life equation V t to the power n is equal to c, V given, t given. So, n and c from these two equations you can find out. Alright. So, you solve these two equations simultaneously, you find out the values of n and c which are constants. Once you found out the values of n and c, then for 90 meter per minute you can find out 90 meter per minute here V, t is unknown to the power c which you found out, okay, sorry n which you found out is equal to constant c which is here. So, from here you can find out what is the value of t. So, similarly you can find out the V if the t is given, same principle, because it is said in the c the speed corresponding to a tool life of 20 minute. So, tool life is given, you have to find out the speed, similar to that you can find out the V is 83.4 meter per minute. Second example is the turning test have resulted in 1 minute tool life for a cutting speed of 4 and 20 minute tool life at a speed of 2 meter per second. Find the n and c values. It is like in the previous case. For data 1 we have the tool life t and then the c is this. Okay. For data V is equal to 2 meter per second which is 120 meter per minute, you find out you have the c and the you have the c. So, find out that V t to the power n is equal to this c, alright. So, you find out what is the value of the n from here by solving this equation. So, at V is equal to 1 which is 60 meter per minute, because in the V t to the power n is equal to c, V velocity is given in meter per minute, okay, and tool life is given in minute. So, here you put this value V here 60, t is unknown, c and n and c will be known, find out what is the value of the t. So, this is easy once you know the formula V t, and formula is very simple, V t to the power n is equal to c which is constant. Third example is a very similar one. In a production turning operation, the work part of 125 millimeter in diameter and 300 millimeter long, a feed rate of this is used in the operation. If cutting speed is 3 meter per second, the tool must be changed every 5 work parts, but if cutting speed is 2 meter per second, the tool can be used to produce 25 pieces between the tool changes. Determine the Taylor's tool life equation. So, you have to find out the T m here, okay, you are converting that into the minute, find out, and then for the second case you also find out the T. Now, the V is given, convert it to meter per minute, because as I said V has to be in meter per minute, and then you put it in the Taylor's tool life equation with the V and T known. Okay. Then with these two equations, two unknown n and c, you can always find out the two unknown values by solving the equation in the way it is shown here. All right. So, these are the simple examples, and you can implement the tool life equation and whatever we have learnt earlier in the form of numerical examples. This is the machine tool that is known. I am not going into very details of this. So, my idea is to study something or to discuss something which is, let us say, these are the holding of the workpiece, particularly in the turning. This is the example of the boring. So, I am not going into details because these are simple things and you must have seen that, you must have gone through in your curriculum. Okay. This is the shaping and planing example. So, whatever we have said, I am just giving you the glimpse of those operations. Okay. This is the shaping and planing machine. Here is the drill and the entire specification of the drill here, and you remember I told you about the point angle. This is the point angle, okay, between the two lips. All right. This is how the drilling is made. This is either through hole, this is the through hole, or it is a blind hole, it does not go up to the full depth. This is the machining operation, which is the reaming, tapping, counter boring, just have a glimpse of it. And this is the milling, where we have the peripheral milling, face milling, slab milling, slotting, end milling. All right. We have the up milling and down milling. You know that up milling means the direction of the milling cutter rotation and the feed are different. Down milling is the same, and these are the specifications, that what happens in case of down milling or what happens in the case of the up milling. These things are common thing, here there is no science behind this. So, you can see this, these are the milling, this is milling machines example, horizontal and vertical depending on the axis of the milling cutter. If it is horizontal, it is a horizontal milling machine, if the axis is vertical, so it is a vertical milling machine. This is broaching example. I have told you broaching in the very beginning, that by that you can make a internal slots or external slots with high accuracy. So, this is the broaching operation, and this is the particular specification that the good surface finish is obtained by broaching. These are the internal broaching, this kind of slots you can make in the as the internal broaching. Now, our idea will be to also discuss the abrasive machining processes, because here this abrasive machining processes differ from the single point cutting tool or the multi point cutting tool like drilling or milling, in the way that here we have a lot of tools, lot of single point tools, and each grain is supposed to be a tool. All right. Now, hard particles like Al2O3, B4C, silicon carbide, they actually abrade the softer material, and that is why the machining process which use the hard materials like aluminum oxide, boron carbide or silicon carbide, they are called the abrasive processes or abrasive machining processes, you know that. Now, the material removal by action of hard abrasive particles usually in the form of bonded wheel. This is particularly in case of grinding, generally used as finishing operations, and in grinding although there is a material removal, but in other abrasive machining, for example, in honing or lapping, the material removal is minimum, but it basically uses as the finishing operation, so that the surface finish can be enhanced. Now, the abrasive machining processes, the grinding wheel has the lot of abrasive particles, as I said. All right. Abrasive particles accomplish cutting, bonding material holds particle in place and establishes shape and structure of the wheel. So, the grinding wheel parameters are basically, there are 5 parameters on which the grinding wheel performance will depend. This is the abrasive type of material, abrasive material, grain size, wheel grade, wheel structure and the bonding material. Okay. So, depending on what kind of abrasive material we are using, either Al2O3 or silicon carbide or diamond, depending on what kind of grain size we are using, okay, rough, bigger grain size or medium grain size or smaller grain size. What is the wheel grade? Grade is the strength of the bonding material. What kind of grade we are using, depending on that we will have the grinding wheel as the hard or the soft. Wheel structure, what is the gap or the void between the grains in the grinding wheel, or the bonding material, either it is a vitrified bond or it is a shellac or it is a resinoid or it is a rubber or it is a metal. Depending on that, you will have the performance of the grinding wheel defined. Let us see, for example, the type of abrasive material, it can have either aluminum oxide designated by A, or silicon carbide C, or the cubic super abrasives are there. There are cubic boron nitride, diamond, etc. Okay. So, aluminum oxide used for grinding steel, ferrous alloys, bronze and other high strength materials, whereas silicon carbide, which is more expensive, used for grinding brittle materials, cast iron, brass, aluminum and hard alloys and the carbides. By aluminum, do not get surprised, because on the top of aluminum there is an aluminum oxide which is very hard. Aluminum itself may not be a hard material, but on that aluminum oxide, that is very difficult to grind, and the carbides which are very hard. So, grain size is expressed in terms of the sieve number. Okay, sieve number is Sn, which corresponds to the number of openings per linear inch. So, if you have a linear inch, let us say here there is 1 inch by 1 inch, okay, 1 inch by 1 inch. So, how many openings you have, that is the sieve number. Okay. And that from that sieve number you can find out the diameter of an abrasive grain, which will be 0.6 divided by Sn, mind it, it is given in inch. So, always you have to convert into micron or millimeter. The largest the size of the grain, the more will be the material removal, you understand that. Bigger grains will remove more material and surface finish will be worse. So, the sieve numbers are given in this way. These are internationally accepted. Okay. 10 to 24, for example, these are the coarse or the bigger grains. 30 to 60 sieve number will be medium grain, 70 to 80 will be fine grains, and 220 to 600 is very fine grain. So, you understand that more the sieve number, since it is inversely proportional, less will be the diameter of the abrasive grain. Meaning that, for example, if it is a 600 sieve number, 600 sieve number will be a very fine grain, because it is given by 0.6 by Sn, which is 0.6 by 600 in inch. So, you can convert that into micron, it will be a very small or very small particle, small grain. Similarly, the grade indicates the strength of the binding material. As I said, when the work material is hard, the grains wear out easily and the sharpness of the cutting edges is quickly lost. This is known as the wheel glazing, meaning that if you have a hard workpiece material and a hard wheel, so since the wheel is hard and the workpiece is hard, the wheel grain, the grains on the surface of the wheel will be very quickly worn out, and since the wheel is hard, those worn out grains will not be dislodged from the surface of the wheel. So, they will stay, worn out grains will stay, and that will rub more and consume more power. This is called the wheel glazing, because the wheel surface then will look like a glazed surface, because they are covered with the worn out grains which are dull grades. They rub more and remove less material, consume more power. So, wheel glazing is not desirable, it should be resharpened, and that layer has to be removed by the diamond pin, as you understand that. So, to avoid this problem, a soft wheel should be used, because in the case of soft wheel, if the workpiece material is hard, the wheel grains will be worn out, but they will be dislodged, because the wheel is soft. And why we want the grains to be dislodged? Because behind the dislodged grain there will always be sharp grains. So, those sharp grains will come out and they will remove more material, they will consume less power. Okay. So, here the specification of the grade is that A to H, these are also internationally accepted. A to H is the soft wheel, J to P is the medium wheel, and Q to Z is a hard wheel. Okay. Now, the structure, like in the case of the milling cutter, between the milling teeth, milling cutter teeth, we have the void or the space, and though that space is for accommodating the chips. So, similarly, in the grinding wheel, between the grains there should be some space that will accommodate the chips, and if the space is very small, then the small chips, anyway in grinding the chips are very small, those small chips will get into the small space between the grains and they will stay there, they will not be able to come out. And then we say that wheel is loaded, there is a loading of the wheel phenomena. Like in the case of glazing, the loaded wheel will not be cutting effectively, it will rub more and it will consume more power, because on the surface of the wheel then we will have the chips embedded. So, therefore, we should not allow the wheel loading, and as soon as the wheel loading takes place, as soon as we see that the power is increasing or the force is increasing, in that case we have to remove that layer by the resharpening of the, or it is called the wheel dressing. By dressing of the wheel we have to remove that layer. If the voids are too small, as I said, then the loading will happen. So, here there are 17 structures 0 to 16, dense to open. 0 is most dense, most densely packed, that means the voids or the space is very small, and 16 is the open, or in between you have the, for example 10. So, 10 will be not very open, not very dense. Recommendations are that for hard workpiece material we should have the closed structure, and for open structure means the voids are relatively large and grains are relatively small. Okay. So, that you understand that if the grains are small, then the closed structure will be there, and recommended when clearance for chips must be provided. Dense structure. So, we said that open structure should be provided. So, open structure should be recommended for chips, for clearance for the chips. Dense structure means voids are relatively small and grains are larger, recommended to obtain better surface finish and dimensional control. Okay. So, for example, dense we mean to say by 12, 13, 14 and so on up to 16. So, those are for better finish and for more dimensional accuracy. Bonding materials, as I explained it to you, that there are vitrified bond, resinoid, silicate, shellac, rubber bonds, metallic bonds, okay. And each of them has a is indicated by an alphabet. Vitrified bond is V, which is strong, rigid, which are commonly used. Resinoid provides the shock absorption and elasticity, they are strong. Silicate provides softness, grains dislodge quickly. Shellac is used for making thin but strong wheels possessing some elasticity, and the rubber bonds they are for making flexible wheels. For example, if the wheel is used for parting of a very thick or high diameter of the workpiece. So, it has to penetrate the workpiece and it should have some flexibility because it vibrates, and if it is very rigid and strong, this will break. So, therefore, this flexibility is given by the rubber bonds and some sort of elasticity is given by the resinoid also. Metallic bonds are exclusively used for the diamond wheels. Okay. Now, you must have seen that each of these is characterized by a number and a letter. All right. For example, abrasive material, here we have an alphabet, next to that we have a letter, next to that we have an alphabet again, then again a letter, okay, letter and so on. So, therefore, the grinding wheel specification, a standard grinding wheel marking system used to designate abrasive type, grit size, grade, structure and bond will be given by this way. All right. So, here we can see that this is the abrasive type, this is the size of the abrasive grain, this is the grade, this is the structure and this is the bond. So, when you buy or purchase the abrasive wheel, nobody will tell you that what is the grade actually, what is the, it will be said like this. Only thing is that should be some kind of an manufacturer's code in the beginning and at the end, and otherwise these 5 will signify that what is the grinding wheel specification. Once again, abrasive type, this is the grain size, this is the grade, this is the structure and this is the bond, kind of bond. Also provides for additional identifications for use by grinding wheel manufacturers. As I said that these will be the manufacturer's code plus these 5 specifications. Okay. So, some of the other things in grinding which are very important and which needs some discussion, that we will do in the next class. Thank you very much for your attention.